we'll talk about this ECG, and most of the cardiac diseases are usually diagnosed on the basis of electrocardiogram. And this is actually an electrical activity that occurs in our heart, and which we record with the help of some devices that is called that machine, and they'll print a trace of electrical activity in a paper, and the process is actually called the electrocardiography, and the trace is the electrocardiogram. So in my class, we'll review the electrical activity of the heart, basics of ECG, and we'll try to read an ECG, and we'll see how we interpret an ECG. And later on, I'll show you some examples of common disorders. Electrocardiography or cardiogram was actually derived from Greek word. Electro means electrical activity, cardio means heart, and graph is to write. So in Germany, they usually write K instead of C. So in some patient, in some textbooks, even you can see ECG being written as EKG as well. So if you want to define what is ECG, then we can say that it's a transthoracic interpretation of electrical activity of heart over a period of time. And this the electrical activity that is occurring during a particular period of time, we record that in a ECG paper. We usually detect by electrodes, which is attached on the surface of the skin, and we record it with a device which is external to the body. And recording thus produced is electrocardiogram, and the process, as I said earlier, is electrocardiography. Usually it is used to determine the cardiac rhythms and condition of the conducting tissues, but we also get information on what is the chamber size, like if there is right ventricular hypertrophy or not, left ventricular hypertrophy or not. Is there any enlargement in the sizes of the atrium? We can get some information on these also, and whether there is a presence of myocardial ischemia and infarction. This is very important, as if you see that, if you feel that if someone says that do an ECG, then literally that means that he or she wants to rule out myocardial infarction, isn't it? So it's very these two terms, like ECG and myocardial infarction, is very commonly used together. But besides that, ECG can even tell us what is its rhythm, what is the conduction of the conducting tissues, as well as the chamber sizes. Not only that, ECGs even can give some idea of the drugs or electrolytes on the heart. Like if the patient has taken digoxin, suppose, then there will be certain changes in the ECG. And if you have hyperkalemia, hypokalemia, or hypercalcemia or hypocalcemia, these are the dyselectrolytemias that can occur, and these can cause some effect on the heart, which we can see in ECG. So it doesn't only mean that doing an ECG means you are diagnosing myocardial infarction, but we get a lot of other information of the heart. This was actually was developed or invented in 1872 by Alexander, but William Einthoven, a scientist from Netherlands, assigned these letters PQRST for the deflections, and he also won a Nobel Prize in 1924 for this. So this was the previous ECG. It looked like this. It was Hughes machine, and look at these things. Okay, these are the electrodes that were developed okay, previously, in two arms, two upper limbs, and one in the left leg. So, but what was the defect of this one was that as it is very big and it is very cumbersome to trace a ECG with this machine, and together with that, they had some problems with electrocution also. So this was not very famous at that time. But nowadays, you can just have a ECG machine a size of laptop, and you can it's like a portable one. You can take anywhere in your ward or anywhere in their place and do ECG with a very simple process. And here they used to put salt water as a electrode solution in both these tanks, these three tanks. So it was very primitive in previous days. And uh, before going through ECG proper, I would just like to recapitulate what is depolarization and repolarization. I think you know this well, that in physiology you have been taught what is depolarization and what is repolarization. If you look at this tracing, then this the in the when there is a impulse, there will be a change in the membrane potential from negative towards the positive one, and this is called depolarization. From A to B, suppose, is a depolarization, and coming towards the resting membrane potential is called repolarization. So depolarization is from A to B and then B to C. This is also called overshoot, and from C downwards, okay, to the D is the repolarization. That is, it is coming down back to its resting membrane potential, and this action itself can stimulate muscles to contract. And so this is what cardiac the repolarization and depolarization cycle is. Why this is important is that in heart you have automaticity, and the resting membrane potential is also in the lower side, around 60s, and it can depolarize spontaneously and then come back to repolarization state. So there will be in a SA node, this is very prominent and it dominates. So SA node produces the heartbeat. Now, so why I was emphasizing in this depolarization and repolarization is that, okay, whenever there is a depolarization, and this you record with the electrode, so if there is a depolarization towards the electrode, then there will be a positive deflection. And when there is a depolarization away from the electrode, then there will be a negative deflection. Suppose, like, this is an electrode, okay, this is a positive, okay, this is the electrode. Now if the depolarization is coming towards this electrode, then there will be a positive deflection in ECG. Now if this is an electrode, and if you look at depolarization is going away from this one, then you will have a negative deflection in the ECG. So if it is in between, okay, then you will have a biphasic one. Because of A, it's a positive, and because of this B, which is going away from the electrode, you'll trace it as a negative deflection. So the combination of these would produce the ECG tracing. So now, whenever there is a myocardial depolarization or repolarization, then waves are produced, and this is recorded as a simple wave. Okay, so there are three main chief characteristics of this wave. We want to describe it with these. Like, one is duration. Duration is in x-axis. This is the duration, and we usually measure within seconds. The y-axis is the amplitude. Okay, this is the height, and we measure this one with millivolts, and then we describe the configuration of this wave. like what is its shape, what is its appearance, whether it's notched or not, whether it's a positive deflection or whether it is a negative deflection, and so on and so forth. So first we describe a wave in terms of duration, amplitude, that is height in millivolts, and then the configuration of the wave. So that is how we describe ECG. Now, a few words on conducting system. And so you know very well that the impulse starts from SA node, then to the AV node, through the internodal nodes. From AV node, it will go into the ventricles. There will be AV delay here, okay, and through the bundle of Fish, then towards the right bundle and left bundle, and again it then goes to the ventricles and divides into Purkinje fibers. Now, what is important in this one is that it starts with the SA node, okay, and then ends in the Purkinje fibers. So the direction of the electrical flow from SA node to AV node to the bundle of branches towards the apex, okay, it's like this. Now, in the interventricular septum, okay, the depolarization occurs from left to right. From this, it's like from the left side towards the right side. The direction would be like that. And in the Purkinje's, it towards the perpendicular to the surface. Okay, so the direction of the depolarization is a little bit different in different areas. And in the ECG paper, okay, if you look at the ECG paper, then you'll see that it's like a graph paper, okay, with small squares, okay, and the large square. And this large square would consist of 5 in the y-axis and 5 in the x-axis and y-axis. So there will be around 25 squares in the one large square. Okay, so it's like, and whenever we talk about time, okay, then we usually set the ECG machine at a rate of around 25 millimeter per second. Okay, so paper speed would be at 25 millimeter per second. So 25 means you have 5, 10, 15, 20, and 25. So a paper will roll in 1 second. Okay, this much of this length of paper will roll in 1 second. So if you now see what is the duration of this 5 Lars, then it's a 0.2 seconds, isn't it? So 1 second, if you divide it by 25, okay, then it's a 0.2 seconds. Now, smallest square would be 0.04 seconds. Okay, you understood this one? Like this is the 25 seconds in 1 second. So this is 0.2 second, 0.2 second, 0.2 second, 0.2 second, and 0.2 second. And if you further look at the smallest square, then it's a 0.04 seconds. Okay. Now this is important because while we describe a wave, okay, we need to know what is the duration of that wave. Like P wave is 0.02 seconds. We said that like that. So what is the duration of QRS complex? Then we count the squares like this. Okay, 1, 2, 3. If it is 1, 2, 3, then it's 0.04 into 3. That is 0.12 seconds. We call it. We calculate it like that. Now in amplitude, okay, this 10 square. Okay, this 10 square height is a 1 millivolt. Okay, so 10 millimeter or 10 squares is equal to 1 millivolt. So in 5 it would be 0.5 millivolt, and the smallest square would be 0.1 millivolt. Okay, so this is what you have to remember in ECG paper and calculation. Okay, now this is what it is. Okay, the 10 millivolt equals 1, paper speed 25 millimeters. Sometimes we go for 50 millimeter per second, then we have to calculate it accordingly. Okay, its large square would be 0.2 and its small square is equals to 0.04 seconds. Okay, so this is what we are talking about. Okay, now while going through this the normal ECG complex, okay, then this is the normal ECG complex. It starts with positive deflection that we call as a P wave. Then there is a straight line. Then there is a complex. This is called QRS complex. This first small or first negative deflection is Q. This is R, and this is the second negative deflection is S. So this is the QRS complex. And there is a straight line again, and T wave is also a positive wave. So you have got P wave, QRS complexes consisting of Q, R, and S wave, and T waves. But there are a few things like the segments and intervals. Okay, now there are a few things like PR interval, QRS interval. Okay, but here it is ST segment, PR segment. Okay, so there's some difference in this one. Now, if you include a wave, okay, in the calculation, then it's a interval. Okay, if you don't include this wave, then it's a segment, like PR segment and PR interval. If you include this P wave, then it's a PR interval. And if you exclude this wave at the end of the P wave to the starting of the QRS complex, then it's a PR segment. Likewise, okay, if you include all the QRS interval, so it is a QRS interval. Okay, now here it's a ST segment because it starts from end of the S to the starting of T wave, so it's a ST segment. In QT interval, it is this whole QRS is also involved, and this whole T wave is also involved. So this is a QT interval. So we have got different intervals and different segments, and these are important while we interpret it. Okay, so if you look at the values of PR interval, then it's around 0.12 to 0.2 seconds. QRS duration would be normally between 0.08 to 0.1. QT interval would be from 0.4 to 0.43, and RR interval from 0.6 to 1 seconds. Okay, there are a few other points like J point. This is the meeting of S with ST segment. This is called J point. This is important. I'll come to that one later in other discussion. And RR interval is from R to next R is the RR interval. Okay. So if you remember this one, I think they have taught you in physiology also, this intervenous triangle. In intervenous triangle, what happens is that, okay, we give limbs as 3 limbs, suppose one right arm, and left leg. Okay, we use 3 limbs, and on each limb we join together, okay, with one with the another. Okay, like right arm, if it is joined with left arm, then it's called lead 1. Okay, right arm with left leg, it's lead 2. Left arm with left leg, then it's lead 3. So lead 1 is both the arms. Lead 2 is right arm with left leg, and lead 3 is left arm with left leg. Okay. Now you should know the polarity over here. It's like right side is always negative. Okay, so in a lead 1, right arm is negative, but left arm is positive. Okay, and left leg is always positive. Okay, so in lead 2, left arm is negative, but left leg is positive. And in the lead 3, it's left arm is negative and left leg is positive. So these are the 3 important leads: lead 1, lead 2, and lead 3. Another lead that we talk about is unipolar leads. This lead 1, lead 2, lead 3 are bipolar leads because they have got 2 poles. Okay, so but there are other like AVR, AVL, and AVF. Okay, these are called unipolar leads. Okay, now unipolar limb leads. Okay, what we do is that, okay, there is a zero over here. Okay, so we consider this one as a zero, and if we attach this zero, okay, with left leg, the left arm, then it's a AVL. If it is with the right, then AVR, and if it is with the left leg, then it's a AVF. Okay, so these are the three another unipolar leads. Okay, which comes together in the center of this triangle, and it becomes zero. This A is for augmented. That means there used to be very small amplitude, okay, if you do not augment this voltage. So it is augmented, and this V stands for unipolar lead. Okay, so this V stands for unipolar lead, and R is for right arm, L for left arm, and F for left leg. So in this unipolar leads, the limbs are always positive and center is negative. So this one is for AVR, this is positive and center is negative. AVL, left arm is positive and center is negative. In AVF, the left leg is positive and center is negative. Okay, so we talked about leads as well, but if you want to define it, then it's like monitoring the voltage changes between electrodes placed in different positions on the body. We talked about unipolar leads. We talked about this limb leads. Okay, unipolar limb leads, AVR, AVL, and AVF. And this V1 to V6 are chest leads. The bipolar leads are lead 1, lead 2, and lead 3. So these two are limb leads. Okay, and this one is V1 to V6 is chest lead. Okay, so these are the two are the limb leads, and this one is V1 to V6 is chest lead. But whenever V is there, remember that it's a unipolar. Okay, and bipolar you don't have that. 1, 2, 3 is Roman 1, 2, 3 is bipolar leads. Okay, so this is what it appears in the body. This is the bipolar leads. Okay, lead 1, lead 2, lead 3, and this is unipolar leads, AVR, AVL, and AVF. The same thing that we talked about in intervention triangle. Now we have put it over the body. It's like this. In the chest leads, okay, we start with V1 to V6, and placement of this chest lead is very important. And V1 is placed in the right fourth intercostal space, just right to the sternum. Okay, and V2 is kept on the same level over here, but on the just left of the sternum, left sternum. So left of the sternum. So this is V1, this is V2. Okay, we don't put V3 first. Okay, we put V4. Okay, we put V4 at the mid clavicular line on the fifth intercostal space. Okay, so and in between this, now we put V3. And in V5, it's on the fifth intercostal space. Okay, but on the right axillary line. Okay, and in the same level. Okay, and the mid axillary line, we put V6. So V1, V2, V3, V4, V5, and V6. This is the normal position of the chest leads. So V1 in the fourth intercostal, but right to the sternum. V2, fourth intercostal space, but left to the sternum. V5, mid-clavicular line on the fifth intercostal space. V3 in between V2 and V4. And then V5 and V6 on the same level of V4, but in the anterior axillary line and mid-axillary line. Okay, so this is how we put a lead, chest leads. Now, this is the normal chest lead. Sometimes, okay, we may have to put it the right chest, okay, to look at the right ventricle, to look at the infarction of the right ventricle. Then it is called the right chest leads. Okay. It's the same, but we start with just opposite way. V1 will be here, V2 will be here. In the V2 will be in the fourth intercostal space on the right. Then we skip V3 first. We put V4, okay, mid clavicular line on the fifth intercostal space, and in between V2 and V4 we put V3 here, and in the same level of V4 in anterior axillary line and mid axillary line. Then it will be a right chest leads. Okay, so this is what it is. Okay, V1, V2, V3, V4, V5, and V6. Now we put R over here if it is a right-sided chest lead. Okay, so if you, this is the V for unipolar. Okay, the 6 denotes that it's a chest lead, and this R denotes that it's a right-sided chest leads. We don't routinely do this one. Okay, we keep this right-sided chest leads to look at the right ventricle only. Now, this is somewhat a little bit the combination of all what we have talked till now. Okay, now this is the you know that these are the angles we have drawn. Okay, now we know that there are these all represents the limb leads only. Okay, so lead 1, 2, this is 1. Okay, this is 2, this is 3, and this is AVF, this is AVR, and this is AVL. Okay, now we call these AVL and 1 as a lateral leads. Okay, now these 2, 3, and AVF as a inferior leads. Okay, and these are other terms of term for leads, because these we call lateral leads because we are looking at the heart from the lateral side with the help of these 2 leads, and we call this one as the inferior leads because we are looking at the heart on the inferior surface with the help of these leads. Okay, so we'll know what is the importance of these nomenclature, because and from where we are looking at the heart, why it is important. Okay, now to know that, okay, we should know what are the contiguous leads. Okay, now 1, okay, and AVL, okay, V5 and V6 are called lateral leads. Okay, these are the contiguous leads. Okay, that means 1, AVL, V5, and V6 can look at the heart from the lateral side. Okay, inferior leads are 2, 3, AVF. Okay, this look at the heart from the inferior surface. AVR is the right-sided lead. Okay, and V1 and V2, okay, looks at the electrical activity of the septal wall of the ventricles, and V3 and V4 are called anterior leads. Okay, so now why this is important is that, okay, now if you have some kind of change in change of myocardial infarction in the ECG, okay, then if these changes are found in V3, V4, V5, V6, AVL, and 1, then we can diagnose that case as a anterolateral MI, because the changes are in anterior and lateral leads. If it's just in the V3 and V4, then we call it an anterior wall MI. Okay, so V4, V5, V6, sorry, V5, V6, AVL, and 1, then it's a lateral wall MI. Okay, now if you have changes in these inferior leads, changes of MI in these inferior leads, then it's a inferior wall MI. Okay, so this is what it is important for. Okay, now let's look at the electrical activity. Okay, I told you that start from SA node. Okay, comes towards the apex. Okay, there is a AV delay over here. In the ventricles, it starts from left to right. Okay, and in the Purkinje fibers, okay, outside towards the outermost of surface of the heart perpendicularly. Okay, so now if you look at the okay this electrical activity from SN node to AV node with the help of this AVR, then what will be the deflection? If you can remember my third or fourth slide, then what I told was, if the electrode is looking at the depolarization, which is going away from it, then what will it capture? It will capture the negative deflection. Okay, but the same deflection, okay, will be captured by lead 1 or lead 2, okay, or AVF as a positive deflection, because these electrodes, okay, are recording it as coming towards it. Okay, so you will have a positive deflections. Okay, but from here in lead 3, it will be just like an in between, isn't it? From here, it will be like it is coming towards it, but after this, it will record it as going away from it. So there will be a biphasic depolarization. Okay, so this is how ECG records electrical activity. Now, in this one, chest leads V1, V2, V3, V4, V5, and V6. Okay, if you look at it here, okay, this green arrows will be recorded in V1, V2 as a positive. This red one also as a positive. Okay, but at the same time, okay, this blue ones, which is actually going away from these lead, will be recorded as a negative one. Okay, so in ECG, you will have a positive deflection of this one, okay, red, negative deflection of this one, okay, blue, and the positive deflection of this green, this one. Okay, so this is R, S, R. Okay, so this is how it will record in V1. But in V6, okay, this red is actually for V6, it's going away, isn't it? So this one is negative deflection. But this blue one is coming towards it, so it's a positive deflection. And this green one is actually this green one, this V6 will look at as if it is going away, so it's a negative deflection. Okay, so this is how ECG records a wave. Now, if you look at it here, okay, like this is the R wave, this is S wave, and this is another R wave. Okay, now in here it's a Q wave, this is R wave, and this is S wave. Okay, so in R wave of R wave of V1 and S wave of V1 are both green. Okay, see, S wave, this R wave of this one, okay, V1, and S wave of V6 is green, which is denoting actually the electrical activity of right ventricle. Okay, blue one here, this is the R wave in V6, and S wave in V1 is blue. Okay, so these are actually indicating the electrical activity of left ventricle. Okay, so and the chest lead goes from V1 to V6. The recording would be different for different waves. Okay, so this I have taken it from Davidson, and I think you can go back to your book and see if again for more explanation. Okay, like this is the blue. Okay, this is black, this is red, and this is green. Okay, so this will now we'll compare with our ECG. Okay, this is the blue one. That means it is activating atria. Okay, and this will produce P wave. Okay, this there will be a delay in bundle. Okay, and this is denoted by this segment. Okay, ventricles are denoted by QRS complex. Okay, this Q, R, and S. Now, repolarization of this heart is T wave. Okay, and repolarization of atrium would be somewhere hidden in this QRS complex, so we won't see that. So P wave is the depolarization of atria. This is the delay, okay, AV delay. It is denoted by this. This is the depolarization of ventricles, now followed by repolarization of ventricles. And in between is the repolarization of atria, which is hidden, okay. So when we go for interpretation of ECG, okay, we should read it in a thoroughly and in a systematic fashion. We try to analyze heart rate, okay, what is the shape, what is the duration, what is the amplitude of P wave, what is the origin of the rhythm, what is the duration of PR interval, and we describe about QRS complex, if its duration, voltage, and whether there is abnormal QRS complex, the axis, intervals, okay, and whether there is R wave progressions or not, and even ST segments. So we describe a lot in QRS complexes. Then we describe T wave, and sometimes U wave is also present after T wave, and we describe that one also. Okay, so we do some measurements, we analyze the rhythm, we analyze conduction, waveform description, and then we come to the conclusion that is ECG interpretation. And the most important thing that would come in is the comparison with previous ECG. Why this is important is that yeah, suppose the left bundle branch block, okay, left bundle branch block is considered as equivalent to myocardial infarction, okay, if it has appeared for first time. Okay, so if you compare the ECG with the previous one, and sorry, and if there is no left bundle branch block, but it is the new onset of left bundle branch block, then that patient will be considered as a case of myocardial infarction. Now, when you compare the ECG and you find that the left bundle branch block was present in the earlier ECGs also, then we don't consider that one as a new onset of left bundle branch block, so it is not an MI. So this is why comparison of previous ECG may be important. Sorry. So this is the ECG tracing. In ECG tracing, okay, there may be manual or automatic. It comes in very different configurations. Okay, some may be 3-channeled, some may be 6-channeled, or some may be 1-channeled. That means in 3-channel you will have 3 leads coming together like this. This is the 3-channel one. Okay, so 1, 2, 3 is coming together. AVR, AVL, AVF are coming together. V1 to V3 and V4 to V6 are coming together. So this is 3-channeled. Okay. Sometimes there may be 6-channeled. Okay. Sometimes there are even 12-channel ECGs also. It depends upon the ECG machine. And what we generally follow the rules are that, okay, these should appear in sequences like this. That means 1, 2, 3. Okay, this will come in first. So if it is a single channel also, then 1, it will be followed by 2 and will be followed by 3. Okay. In this in this group also, the AVR comes first, AVL, then AVF. So after 3, AVR will come, which will be followed by AVL and AVF. So from here it's V1 to V6, V1 to V2, V3, V4, and V6, like so on. So this is the sequence that it comes in as a rule. And sometimes, okay, there may be a rhythm strip like this. Okay, here it is of lead 2. It is we are recording lead 2 as a long lead. Okay, this is called rhythm lead. And sometimes in other, it may be a V1 also, but usually it is taken off lead 2. So lead 2, you have a long strip of lead 2 where we can analyze the rhythm. So this is called rhythm lead also. Now in ECG, what you'll find are this speed. What is the speed of the paper? It's 25 millimeter per second. What is the voltage that has been calculated? Okay, in limb leads it's 10, in chest lead it's 10 millimeter per millivolt. Okay, so these are very important information that will be printed in ECG paper. And together with that, you'll have name, age, sex, and even a time of recording, because ECG is actually a dynamic recording of a dynamic process. So time is very important. You may not find anything in ECG just right now, but after 6 hours, there may be changes in ECG. So time is also very important in recording. Okay. So next thing, if you have noticed, then there is a marker, something like this over here. Okay. What this designates is same as this one. Okay, 10 millimeter per millivolt. If you count this small square, there will be 10. Okay, so this is a 10 millivolt per millimeter per millivolt. Okay, so this is in the normal calibration. Now, this also indicates that the stylet are also in good condition. Okay. Now, sometimes in some other ECGs, what you may find is that this may be of 5 only. Okay, not of 10. Okay, that means the recording has been done in a half amplitude. Okay, so the amplitude that has been shown in this graph is not correct. Okay, so for correct amplitude, you have to multiply by 2, because 5 into 2 is 10, isn't it? So here also you'll have to multiply by 2. Suppose this is 5, okay, and amplitude is here 1, 2, 3, means that is 30. But if this is 5, then you should multiply this one by 2 also. Okay, so the actual amplitude would have been 6, because it's very large, okay, and cannot be traced in a graph. It has been done in a half caliber. So to calculate the amplitude, you should first of all see